Hello and welcome to Easy Projects. Today we will go through how to make a simple adjustable power supply out of the LM317 voltage regulator. Or in this case I use the LM350, but it's almost the same and the calculations will be the same. The power supply will be capable of delivering a voltage between 1.25 and in this case 28 volts. But the regulator can go all the way to 37 volts, so if you have a transformer that's outputting that much, then you can easily make that happen. So let's start by taking this power supply apart so you can see how I have built mine. You can make up your own mind how you want to do yours. Ta-da! So the most important things we have in here is the transformer and the voltage regulator. But of course we need a bit more. We have the mains power coming in down the bottom there, then going to the on-off switch, then goes to the fuse, goes to the transformer. Then from the transformer secondary windings we have this tap select switch, so we can select between 12 and 24 volts. This gives us 14 and 28 volts in DC. We then have the wire going to this main board down here with some rectifying diodes to make a bridge rectifier. We have 2 input filter caps. We have the rest of the circuitry for the regulator, and we have the regulator itself mounted on this heatsink with a little fan on it. Then we need a potentiometer to control the voltage. This is a 10 turn pot, I highly recommend that, but you can use a single turn if you want. Then we have a voltmeter to measure the voltage, and we have our binding posts down here. And we then have a load switch to turn the output on and off. And I also have a 12 volt regulator for the fan, a little diode and a capacitor over here, just kinda botched in there. But there was a secondary winding that I didn't use on this transformer, so I used that for the fan, so I don't introduce any unwanted noise to the rest of the power supply circuitry. And let's just take a look at the back and see what we got here. Then we just have the mains input again, the power switch, the fuse and the tap select switch on the transformer. There you can see the back side of the voltmeter and the pot and the on-off switch for the output. So when I first designed this, I had the regulator mounted on the board down here, but the heatsink on it, and that didn't last very long. It broke off eventually, and so I ended up by just gluing it to the bottom of the case down there. That seems to hold. So to get to how to build one of these, I have the schematic and board layout and everything on my website, so you can download that. There's also a text version of how you build one of these if you prefer that. But you will probably prefer to just watch the video, so let's find the datasheet for the regulator and see what we can come up with. We might as well take a look at what made me choose the LM350 in the first place. This was the first power supply that I built, and when I made it I had very little knowledge about electronics. So I searched around the internet for some simple voltage regulators, and I found the LM317, but I noticed that it's only capable of 1.5 amps, and I went to my local component distributor, and I asked him if he had something similar to the LM317 that will give me about 3 or 5 amps. So he had the LM350 that was almost as cheap as the LM317, and he had this LM338. It's in a TO3 package, and this was much more expensive, so I didn't buy that one at the time. I chose the LM350. There's not very much of a difference between the LM317 and the LM350, except that the LM350 can deliver 3 amps, and it's only capable of going to 33 volts, where the LM317 can go to 37 volts. Also, the input-output differential voltage versus the output current is better on the LM350. So if I have an input of 30 volts and an output of 5 volts, then I can maybe deliver, we can take a look at the curves in a minute, but if this one can deliver 1 amp, this might only deliver 300 milliamps or thereabout, I don't know. But that was something I didn't know about at the time, so I had a little experience with the regulator shutting down and all kind of weird stuff. So that's something you learn when you play around with these things without knowing what you're really dealing with. But I managed to make a power supply out of this regulator, and that's why I chose it to be the one I will talk about in this video, because it is very easy to use. So if we take a look at the LM317 datasheet, we can get an overview of what we need to make it run. As I said, the output voltage ranges from 1.2 to 37 volts, and it's capable of delivering in excess of 1.5 amps. The line and load regulation is better than 0.1%, and it's a floating regulator, so you can use many in series if you want that. And also it's not about the input to ground voltage, it's about the input differential voltage, so you can have maybe an input voltage of 50 volts as long as your output voltage stays within 37 volts of that. It has complete series of protections. This is very important for us because we don't want the power supply to blow up if we accidentally short the output or something like that. It has thermal shutdown and safe operating area control. And the regulators are monolithic integrated circuits in TO220 and so on packages, intended for use as positive adjustable voltage regulators. And here's something important: the nominal output voltage is selected by the means of only a resistive divider, making the device exceptionally easy to use and eliminating the stocking of many fixed regulators. But in this case we just want to use it as a variable supply. So we have skipped on to page 3 of the datasheet, and here's an example of a typical application. This is a basic adjustable regulator, and that is exactly what we want. But we're going to add a little extra circuitry, some input and output caps, and some diodes and a capacitor from the adjust pin to ground. So the way this regulator works is that it have an internal reference of 1.25 volts. It will have this reference across the adjust pin and the output. So by putting a fixed resistor across there and then a variable resistor to ground, we can change kind of the feedback voltage to the regulator, and it will rise the output until the input matches the reference. So in this electrical characteristics table for the regulator, we find all sorts of parameters that give us some specs and information on the regulator. There's some important things in here, like a minimum load current and the reference voltage we talked about earlier. from up here. This minimum load current is one of the things that affect this resistor R1, which we have to choose later on when we are designing the circuit we want to use. Because if this resistor is too high, then there's not enough current going to ground through this resistor, and then the output cannot go all the way down to 1.25 volts. If there's nothing connected to the output, of course. And we of course have to look at the right table, because this is only for the LM117 and 217. So if we take the next page, we can see that actually the minimum load current has changed from 5 milliamps max to 10 milliamps max. So if we design it for 5 milliamps, then it might not work on the LM317, because it can need as much as 10 milliamps. And if we take a look at this graph I talked about earlier, about output current versus input output differential voltage, you can see that we can only have an input-output differential voltage of about 15-17 volts if we want the full 1.5 amp output. If we go above that, then the output current will drop off. So this is one thing that's better in the LM350 regulator. If we want an output of 1.5 amps, then we can use the whole voltage range. And if you want the 3 amp output that it's capable of, it will be around 15 watts in difference between the input and output. But another thing is to get the heat away from the regulator. If we start to dissipate huge amounts of watts in it, it will go into a thermal shutdown anyway, because it's overheating. Another thing to care about is the dropout voltage of the regulator. The input have to be a few volts over the output voltage at any time for the regulator to stay in its regulation. So if we do not meet this requirement, then the output will start to drop when we put a certain amount of current through the regulator, and we don't want that. So this dropout voltage is affected both by the temperature and the output current. So as we can see here, the lower graph is for 20 milliamps and this upper one is for 1.5 amps. The x-axis is the temperature and the y-axis is the voltage drop, or the dropout voltage. So if we kind of take the highest possible dropout voltage for the regulator, that is 2.5 volts. So if we keep our input 2.5 volts over our output, we should not get any problem with the regulator dropping out of its regulation. So we'll keep that in mind when we design the circuit. So another thing is this power supply is not going to be very stable on the output if you draw a huge amount of current out of it. Or it will stabilize, but if you set it to 10 volts and then you hook up a 1.5 amp load, then the output voltage will start to drift a little until the temperature has settled inside. And this is something to do with the reference voltage versus the junction temperature and all the other components in the regulator. And we will measure that when we start doing some tests of the power supply. This will still be usable for most electronics works anyway, so but if you need some very fine and stable output voltages, maybe you shouldn't use the LM317. So to calculate the output voltage from this regulator, we are given this formula here. That's V out equals the voltage reference times 1 plus R2 over R1 plus I adjust times R2. And they are saying that the device is designed to minimize the term I adjust, 100 microamps max, and they're saying that in most cases we can just delete this and just use this. And since we are probably using 5 or 1% resistors anyway, then this gets much lower than our other tolerances. So In this case we'll just forget about this. It doesn't really matter that much. As said, we will be using the typical application circuit from this datasheet, and they state that the performance may be improved by adding capacitance as follows: an input bypass capacitor of 0.1 microfarads, an adjustment terminal to ground capacitor of 10 microfarads to improve the ripple rejection of about 15 decibels, a 1 microfarad tantalum or 25 microfarad aluminum electrolytic capacitor to the output to improve the transient response. And in addition to external capacitors, it's good practice to add protection diodes as shown in figure 5, and we will also do that. So as a funny little detail, we'll take a look at figure 5 again. As they claim will show the protection diodes. I can't seem to find any, but I found it in figure 8 instead, so we'll take a look at that one. So we have this diode up the top here that will protect against shorts on the input, so the output capacitor will not discharge back through the regulator. And this one will protect against this capacitor on the adjustment pin, so that cannot discharge through the regulator. In a datasheet from another manufacturer, they are claiming that these diodes are not necessary if the output current and output voltage is not in excess of some limit, but we will put them in there anyway. So this circuit is in fact the thing that we will be building. We'll need to add something on the input here, and we'll need to add something on the output as well. Since we're using a transformer to deliver the current to this regulator, we will need to rectify the AC so we get a DC signal, and we'll need some input capacitors to reduce the ripple on the input. On the output we'll need a load switch, we'll need some binding posts, and we will need a voltmeter so we can read the output voltage. We could also add a ammeter if we want that, so we can read the output current as well. And just to sum up, we will have to take a look at the transformer, the rectification, the input caps, the two divider resistors to set the output voltage. We'll need a heatsink, and we'll need some panel meters to show us the voltage and current outputs. For the rest of the circuitry we will just use what they have specified in the datasheet. You can find the exact schematic I have been using on my website easy-projects.com, and it's all the way on the bottom of the page when you select the simple adjustable power supply. So this is basically just what's in the datasheet, but I've added the bridge rectifier, the input caps, the output caps, and all the rest of the circuitry. I have also labeled all these components so they match the component designators on the PCB itself. You can also find the board layouts, the component overview, some drawings of the transformer wiring and the board I have been making. And again, I have mounted the regulator and the heatsink on the board, and it's just held in place by the solder joints on the regulator, and that's not how you're going to do it. But we will get back to that, and I have a much better idea of what you can do to still have the heatsink on the board if you have the need for that. And I have done some experiments with the input filter cap values, and we will also do that in this video. There's some values for the potentiometer and the R1 resistor versus different output voltages. There's something about heatsinks, how to calculate the size and values of the heatsink. And most important, there's the materials list and a nice picture. And yes, it took quite some time to get it to 3.300 on the multimeter. Now that we know what we need to look at, we can start to do some calculations. And if we start with the transformer all the way at the input side, we can then slowly move across to finish at the output. Let's start by taking a look at the transformer, because this is where we'll get our power to the regulator. There's many different types of transformers, but you can use pretty much anything you want. There's these standard types of transformers. I think they're called H-frame or something like that. And this is basically the same as this one. This is just a PCB mount version. And then there's these toroidal transformers. Now, which type of transformer you get does not really matter, but the important thing is that it is rated for your mains voltage. And here in Denmark we have 230 volts at 50 Hz, so this transformer will be capable of that. You can see the secondary winding is 2 times 12 volts at 3.3 amps AC. This means that we can either use these as 2 separate 12 volt supplies, or we can make one 24 volt. Or we can make a combination of those, so we can get a lower voltage when we're using a lower voltage on our power supply, so we don't have to dissipate as much heat in the heatsink. But we'll get to that in a minute. It is of course important that you don't exceed this maximum current rating on the transformer, because then the transformer will get hot and it can actually melt and short out and start a small fire. You don't want that to happen. Now, this transformer does only have one secondary winding and one primary winding, and the way you can tell which is which will be that since this is a step down transformer, and I know this is rated for the mains voltage, then the fine wire on this side will be the primary winding, and the coarse figure wire on this side will be the secondary winding, because the voltage will drop equally to the ratio of the turns. So if you have this is a 24 volt transformer, so if we had 240 volts going in and 24 volts going out, it would be 1/10 of the turns on this side than on this side here. If you don't have a confidence in working with mains electricity, you probably shouldn't use a transformer. You can then use one of those AC to DC break adapters that come with laptops or printers or something like that instead of the transformer. You'll then just wire those across the plus and minus DC on the board instead of the AC. And that's these two nodes here. So you're just skipping the rectifying part of the circuit. But you can do that when you're using a DC input. If you are going to buy a transformer, it's a good idea to get one with a split secondary winding, like I showed you with the toroidal transformer before. And it can be either one of these two types here. Now, this type thing is just something I came up with, but you can get a transformer where the winding is just split with and only a single wire is coming out in the middle of the transformer here, or you can get one with two separate secondary windings, and this type is the most common one, but these do also exist. Now, which one of these you get doesn't matter, because we are going to make it into one of these anyway by connecting the two center conductors here. And we're gonna connect them in a way so we can select between 12 or 24 volts if that's the case with a toggle switch. So the way we can do this is very simple. We have one end of one of the secondary windings going directly to the board, and the other end of that winding combined with the first end of the next winding will go to one position on the switch, one of the on positions, and the other end of the second winding will go to the other on position, and then the common position on the switch will go directly to the board. So when you flick the switch, you will just either use that part or the whole transformer. But you can also do some more advanced stuff where you can put multiple windings in parallel and stuff like that, but we won't go into that because there's risk of getting unbalanced load and you can melt down your transformer, so that's not a good thing. In this case my transformer was still capable of delivering all the current I needed with one of the windings, so I didn't bother to do that. But you can look that up if you want to make yours like that. And on the primary side of the transformer you always want to add a fuse, and you probably want to have a switch as well so you can cut the power to the whole thing. But if your transformer doesn't have a split secondary winding, then you don't have to worry about all of this. You will just have the two conductors going to the board. And you can also add a fuse on the secondary side here as well, if you want that. So when you have your transformer in place, you will have a signal that looks like this from the output of the transformer. And this is an AC signal, and of course we cannot make a DC power supply out of that, so we use a bridge rectifier to get all the negative voltage kind of flip over to the positive side. And we will build up a little experiment to experiment with the capacitors. We need to flatten this out because this doesn't make a very good power supply either, because we have all these bumps that go all the way down to 0 watts. I have hooked up the transformer to the mains electricity, and I have put in the rectifying diodes, and we have the regulator here. Don't mind all the rest of this, that is just for something else I am working on. So I put a fuse in series with the transformer, just so if anything should touch each other, then we won't destroy the transformer or melt down any wires or anything. Let's first take a look at what the signal looks like when we measure it directly on the secondary winding of the transformer. So this is a 24 volt RMS transformer, and we can see we're getting 28.7 volts RMS AC out of this, and when we load this with 3.3 amps, I'm pretty sure that would be almost 24 volts. But they do drop in voltage when you load them, so that's something to take into account. And we can also see that the peak-to-peak voltage is 80.8 volts, so it's not something you want to play around with if you're not careful. So let's see what happens when we look at the signal on the other side of the bridge rectifier. So we'll turn off the power here, and we will move the ground lead and the probe to the other side of the rectifier. And we'll try to turn on the scope again. You can see that's way out of range here. So there's something wrong here, that we'll just put a little bit of a load on there. So I've just put a 12K resistor across the ground and the positive. And now we can see that the waveform has been flipped so that the negative now is also a positive signal. And we can see that our peak-to-peak voltage is now a little under half of what it was before. This is because there's a little bit of a voltage drop over the rectifying diodes. But that's nothing to worry about really. It's about 0.6 volts for each diode, so we have two of those in series and we will get a 1.2 volt drop. So if we just change the time base a little here, we will be able to see the difference it will make when we put in this filter cap. We'll just turn off the power again so we don't short out anything. And now we can see what difference that makes. Now we can see that 100 microfarad capacitor made a huge difference in the amount of ripple we got here. It's almost disappeared. And if we change this to AC coupling and change the volts per division, we can center this, and you can see that there's about 320 millivolt ripple with that 12K ohm resistor in there. That would be perfectly fine for power supply, but the problem is that when we put a huge load on this, then the 100 microfarad capacitor will just be discharged to 0 volts and then charged up again at the next power cycle. So just by changing that resistor, we will see that this ripple will get much worse. So I'll try to find something with a little lower value so we can try to put that in there. So now with a 4.7K ohm resistor in there, we are already getting 720 millivolts of ripple, and since that will give us 8 milliamps of load, and we'll need to be able to draw well over 1.5 amps out of this, so we will need a lot more of input capacitance. And there's formulas to calculate the value of the capacitor we need. So if we say we want a maximum of 2 volts ripple at a full load of 3 amps on our power supply, then we can calculate the capacitance needed to obtain that. And that formula is not very difficult at all. Assuming that we have our capacitors charged to the maximum voltage each time, we can use this formula that the ripple voltage, or the difference in the voltage, equals the amps that you're pulling out of them divided by the frequency of the charge of the capacitors. This is the mains voltage times 2, because we are rectifying it through the bridge rectifier, so we get all the negative peaks flipped up, so we have the double of the frequency. And this is times the capacity, or the capacitance. But since we don't know the capacitance, but we know the ripple voltage that we want to obtain, then we can flip these around, so we can calculate the capacity from the drawn current divided by the frequency times the ripple voltage. So to get 2 volt ripple voltage, we will need a 15 millifarad capacitor, or 15,000 microfarad. And you can easily get 10 millifarad and 4.7 millifarad, so that's probably what I would use if I had to design this today. And when I built this, I used 6.8 millifarad, so that's just over half of this, so I could expect 4 volts of ripple in my power supply. And this ripple voltage is important when we have to calculate the resistive divider for setting the output voltage. if we set the output voltage above what our voltage at the minimum voltage of the capacitor, so that's the voltage in minus the ripple voltage. If we set the output above that, then the output will start to have the ripple as well when we draw enough current, and we don't want that, so we have to set the output voltage below this level, if we could say. So the only problem with these 10 millifarad capacitors is that they are quite large, and I don't think you will be able to fit these in the board I have designed. So if you want to use this large capacitors, you have to do your own board. But I used one of these 4.7 millifarad capacitors and 2.2 millifarad in my power supply, and it seems to work fine, but you'll get a little more ripple current. You could maybe fit 2 of these in there, but I'm not sure. And I don't know if you will be able to get a 10 millifarad that's kind of have a smaller footprint and will be a little higher, but it can also work with the probably 6.9 millifarad. So if you wanted to use the LM317 voltage regulator, we had a problem here because our input voltage will be too high. Even if we subtract the minimum output voltage of 1.25 volts, we still have an input-output differential voltage of about 36 volts. And that's 3 volts above the specified value. But again, the LM317 will be capable of 37 volts input-output differential voltage. And there you can also subtract the 1.25 volts. So this will be just suitable for the LM317. I have now connected the regulator to the rest of the circuit and added a potentiometer and a resistor. And we will go into the calculations of these in just a minute. But first I want to show you what will happen if you set the output voltage higher than the input voltage minus the ripple voltage. We are now at 4 volts at the output, and we can turn the potentiometer to rise the output voltage. And you can see when we hit the about 34 volts, it's starting to get into the ripple. And with these resistor and pot values I have chosen, I still have about 1/8 of a turn on the potentiometer. So we will need to find a value for the resistor and the potentiometer so that we will not get into this ripple at the top of the voltage range. So to calculate the resistor divider values, we will need to know the maximum output voltage from the regulator. And we know that the output voltage from the transformer is 24 volts RMS, and that is 33.94 volts at the peak of the waveform. And to calculate the maximum output voltage, we take this voltage and we subtract the voltage drop over the bridge rectifier, and we have a 2 volt ripple on the input filter caps, and then we have the 2.5 volt dropout voltage of the regulator. And so that gives us 28.24 volts as our maximum output voltage, and this will be at a full load of 3 amps. So if you're using the LM317 regulator, you can maybe get a little more out of it, because you only need to calculate with 1.5 amps instead of 3 amps, so this will only be about 1 volt instead of 2 volts if you're using the same input filter capacitor. So now that we know our maximum output voltage, we can calculate these two resistor values here. And with the resistors I have in there now, the potentiometer and the fixed resistor, we are able to get an output voltage of 36.66 volts, and that was about what we saw on the scope before. And compared to the 28.24 volts, this is way too high, so we need to change one of these two resistors. And the potentiometer is not that easy to change, so we will change the fixed resistor to a value that will match the desired output voltage. And we can find the new value for R1 by using this equation here, which gives us 236.2 ohms. I was using a 4.7 k ohm potentiometer, but it measured 5100 ohms, so I used that value instead. And we will not be able to find a 236.2 ohm resistor, so we will use a 220 ohm and a 15 ohm in series. And we'll be out by 1.2 ohms, and that will be just fine. So I changed the resistor R1 to the 235 ohms, and it was a little bit over. It was reading 28.9 volts. So I changed the 15 ohm resistor to a 18 ohm, and now let's see where we are going to have our maximum voltage. And now it's 28.4 volts on the scope, at least. It could be a couple of hundred millivolts out, but that's not far away from our 28.24 volts. Now we should be able to load this with 3 amps, and the output should stay clean and free of any ripple. But there's something else that we can take a look at if we wind the pot all the way down. We might just be able to see here on the scope that it will start to kind of oscillate down in the bottom here, like that. So if we change the scope to AC coupling, and adjust the time base, we can now see that we have this oscillating signal at around 6 megahertz, and that's about 1.4 volts peak to peak. So this will not make for a really good power supply. But you might remember that we did not put any output capacitors on this regulator. So I'm pretty sure if we put the 25 microfarad capacitor in there that they recommend in the datasheet, we will see this oscillation disappear. And I'm about to connect the capacitor right now. But if we turn the vertical scale all the way down, you can see we still have these spikes, and the frequency is measuring 100 Hertz. So that's the double of the mains frequency, or it's the same frequency as the signal we have after the bridge rectifier. So my guess is that this is the ripple from the input of the regulator getting through to the output. Now there's not much load on this regulator, but as you might remember, I did put a 4.7 k ohm resistor across the input filter capacitor to act as a load when we measured the rectified signal. So let me try to remove that 4.7 k ohm resistor. And you can see this ramping has gotten lower in amplitude. And there's also a figure in the datasheet specifying how much of the input ripple will get through to the output. And this, now we have about 20 millivolts of ripple, and I guess that's about normal. So this is the line transient response for the LM317 voltage regulator, and you can see if we have an input voltage change of 1 volt, we will have an output voltage deviation of about 1.25 volts with a 1 microfarad and a 10 microfarad capacitor on the output and the adjust pin. And I put a 22 microfarad on both, so we should see a little better than this. And of course this is for the LM317, and we're using the LM317, so it could be slightly different. But it's not far off what we're seeing from the scope here. And as we saw when we measured the ripple on the input, we had about just under 800 millivolts of ripple with the resistor in place. So this will be another reason to have a high amount of input capacitance. As we increase the load, we will have more ripple on the input filter caps, and that will result in more ripple on the output. So the more input capacitance, the better. So the next thing to calculate on the list here is the heatsink. And I also have an example of that on my website, so we can take a look at that. So the power dissipated in the regulator will be equal to the difference in the input and the output voltage times the current. So if you have an example of 24 volts in and the lowest setting of 1.25 volts out, that's a difference of 22.75 volts. And you times that with the current and you get 34.125 watts. So you will need a heatsink that has low enough thermal resistance so that the regulator will not overheat. But 34 watts is a lot of power, and that's another reason why we need to have a tap select switch on the transformer, so that when we're working with the lower voltages we can select an input voltage that is half of the maximum, so we will not dissipate as much in the heatsink. So if we lower this V in to 12 volts, then our difference will only be 10.75 volts, and we'll have just over 16 watts to dissipate instead of 34. And by adding a fan to the heatsink we can lower the thermal resistance by a great amount, so that's a good idea to include a fan in your design. The thermal resistance of a heatsink tells how many degrees it will rise in temperature if you put 1 watt into it. And of course a smaller heatsink will heat up faster than a larger heatsink. And of course by blowing air through the heatsink, that will cool it down, and therefore the thermal resistance will be lower. Usually the datasheet for the heatsink tells what the thermal resistance is, both with passive cooling and with active cooling, where the active cooling will be where you blow air through it with a fan. And for this power supply you will probably need a heatsink about this size, or maybe a little larger, if you are using a fan. If you don't use a fan, then you'll need a larger heatsink, if you're going to draw a lot of current over a long period of time. And the only thing left on the list is the panel meter. In my power supply I used one of these cheap voltmeters from eBay, and they seem to work very well. They have an adjustment part on the back, so you can trim them for the best accuracy. There's only one decimal place on these meters, and they can go to 99.9 volts. But they are accurate to that decimal, so that one decimal place over the entire range, so I'm quite happy with these. And if I remember correctly they cost under $4, so that's nothing really. But you can of course use one of these old school analog meters. This is kind of a blank 500 microamp ammeter, but can also be turned into a voltmeter. But you can of course also make your own volt and ammeter by using a microcontroller and using the built-in ADC. I'm working on this little board where I have a PIC 16F616 reading the voltage directly with the ADC and reading the current through a current sense amplifier. And you might have seen this board in my PCB manufacturer tutorial. And I will also make a video of this project when it's finished, and the schematic and board layouts will be available on my website once they're done. And tested, of course. But the idea with this was that it should be small enough to fit on the back side of one of these 16:2 LCD displays. You can also get one of these 4.5 digit voltmeter chips that will put out a binary coded decimal signal, and you can then decode that with a BCD to 7 segment or LCD decoder, and then you can use an LCD or 7 segment displays. And just remember with these digital panel meters that you'll need one that has the separate sense wire, because when you're going down to 1.25 volts you don't want your display to dim out. I think this will work from, here we have it, it will work from 4.5 to 30 volts, and it can measure DC from 0 to 99.9 volts. So we have to power this from the non-regulated side of the power supply, so right after the input filter caps, but they go way higher than 30 volts in some situations. So what I have done is, since this uses very little current, I have just put a Zener diode in series with the positive lead, so that when the tap select switch is on the high, then it will not go over the 30 volts, and when it's on the low it will still be over 4.5, and that way we don't fry the back end out of this meter.